So yesterday we talked a little bit about the beginning part of this. So this is a worksheet where we're going to start to do quantitative problems with our force diagrams and get to the point where we can actually solve problems with our force diagrams. And sometimes we might use trig and sometimes we might not. So for these three problems that we did yesterday, what we did first is draw our force diagram, and then using the relationships that we talked about. Oh goodness, that was before break, where our force due to gravity is mass times acceleration due to gravity. We know that on Earth, acceleration due to gravity is minus 10 meters per second. And the units that we're going to use then is for mass, we're going to use kilograms, for acceleration, meters per second squared. And that's going to give us the units newtons for force. And so we did these three problems where we set up a force diagram for each problem and then used that to find in each of these cases the tension that was in the cable above the masses. So we had two where we just had a single object that was hanging. The first one we had one cable and the second one two. And then down at the bottom we had two masses that were hanging from consecutive cables, kind of in a chain or string. And we solved for both of those. And did anybody have any questions about those before we go on? No? Okay. So on the next page, we start to see things where we have forces that are happening at angles. We have anybody in the fishing club? No. It's like the perfect social distance activity. I'm shocked because nobody yesterday wanted to talk about the fishing club either. But the first thing that we're going to do here is take a look at what's going on and draw a force diagram for the situation. Our instructions actually ask us to find the horizontal and vertical components of the tension in the fishing line. So you guys probably are aware that at the end of the fishing line is a fish having a terrible day. Right? He's very surprised because now he thought he was going to get a free lunch, and instead he's being abducted by aliens above the surface. Anyway. So the first thing we have to do is figure out what forces our fish friend here is experiencing. So what do you think? What forces is he experiencing? Anybody? Yeah, go ahead, Michael.
Pull.
Yeah, he's got that pull from that line, right? Is that the one you meant?
Yeah.
Yeah, so he's getting pulled sort of up into the side, and that has the amount of force there is 38 newtons of force. What about what other forces every object on Earth experience? Gravity, yeah. Is the fish sinking to the bottom of the ocean? No, fish don't usually do that, right? We're not given a mass for our fishy friends, so we're not going to be able to figure that out. But this just asks us to find the horizontal and vertical components of the tension in the fishing line. So in order to do that, what we're going to need to do is think about how to break this into a vertical component and a horizontal component. So one thing to think about is that there's going to have to be some kind of axis here. It's helpful to use an axis that's based on forces that are already in your problem. And so gravity is frequently a really good one. So I'm going to draw two axes there that kind of indicate where my axes are. So if I'm trying to figure out a vertical component, it's going to be along this line, and a horizontal component is going to be along this horizontal line. Now, remember yesterday, yesterday when we were doing trig problems, we were talking about drawing rectangular boxes around things. So for this guy, our rectangular box is going to have this diagonal force across the diagonal of that rectangle. And then we're going to draw sides that are parallel to the sides of where my axis is. And so I'm going to kind of look at this. So I know I should have a horizontal line that goes across from the top of my arrow. And I should have one that goes down. So there's my rectangle. And then the sides of that rectangle are going to be my vertical and horizontal components. So I'm going to end up having a component of that force there and a component there. And like we talked about yesterday with our rectangles, this side is equal to this side. Both of the vertical sides are equal in magnitude and the same direction. And the same with our horizontal piece. We're also given an angle down here. We're told that the line's being pulled up at 55 degrees to the horizontal. So we know that this angle has to be 55. I know it's really tiny and hard to see. I'm going to redraw this a little bit. So I'm going to draw just the part of my triangle that I'm concerned about. All right, so there's my triangle. And just like our fisherman is pulling that string up and to the right, we have an up component and a component that's going to the right on our triangle down here. And then the sum of those two vectors is going to be the diagonal line that's going across. We've labeled 38 newtons here because that's what we're told in our problem, that diagonal pull on the fishing line is a 38 Newton force. So we need to solve for our horizontal component, which I'm going to call x, and our vertical component that I'm going to call y. And those are our two unknowns, and we're going to use trig to solve those. If we've got this triangle, we know that we've got a right angle in here. So this side is going to be our hypotenuse. The x side is going to be the adjacent side to the angle that we know. And the y is going to be the opposite side. Now, when you guys solve these problems, you may not choose to use this rectangle down here, or sorry, this triangle down here. You may want to use the one that's kind of above, and that's okay. You're still going to get the same answers. As long as you're careful about what your angles are and what your sides are, you should end up with the same magnitudes for those component vectors. All right, so if I want to solve for x first, what I know is my hypotenuse. I'm solving for the adjacent side, and I have an angle. So for x, what I'm going to do is, let's see, I'm going to just kind of move this around a little bit. I'm going to say the cosine of 55 degrees is equal to x, the length of that side of the triangle, divided by 38 newtons. So x is going to be equal to 38 newtons times the cosine of 55 degrees. Grab my calculator. Again, if you're using your same calculator for math, you may need to make sure you switch to degrees. I got that the magnitude of the sideways force is going to be 21.8 newtons. And then if I solve for y, I'm going to need to use the sine of 55 degrees because I'm looking at the ratio of the opposite to the hypotenuse. So I'm going to use sine. So y is equal to 38 newtons times sine of 55. Let's see, 38 times sine 55. So for that side, I got 31.1 newtons. So our fish is being pulled up with 31.1 newtons and to the side with 21.8 newtons. So if our fisherman wants to get this fish out of the water, the fish better have a mass of less than 3 kilograms. Did you guys catch that? Because if we have an upward force that's 31.1 newtons, that's going to be the force that's opposite of gravity. So if I stick this right back here, 31.1, because this upward force is going to be the same as this downward force. Actually, if it's the same, he's not going to come out either. It has to be just a little bit more, or else he's going to have a hard time pulling him up. And then the x component of that force is going to be 21.8 newtons. So there we go. We solved both sides. Do you guys have any questions about that one? You want me to do another one? Yeah. Okay. So for the next one, we've got a suspension bridge. That's just a bridge that has cables that hold up the platform that the cars drive on. It's connected to an anchor at a 20-degree angle. We need to draw a force diagram for the anchor and then find the vertical and horizontal component forces on the anchor by the cable. So we've already got a little bit of a sketch here about what we expect to be happening. So I'm going to just copy some of this. There's my anchor. I've got a cable that's pulling up into the side with 1,500 newtons of force. And we need to find the horizontal and vertical components of that force. So I'm going to draw my axes first. I can label my angle there. If I'm going to try to solve for a vertical and horizontal component, I need to figure out where those go on my sketch so I have a good triangle to work with. So what I'm going to do is use my vertical and horizontal line from my axis to draw a rectangle so I have two triangles to work with. So I know I need a line that's parallel to my horizontal and parallel to my vertical. So I'm going to draw that with my blue marker here. So there's my rectangle. And my vertical and horizontal sides ought to be something like this for my horizontal, and this guy for my vertical. And each of those are equal to the other side of that rectangle. So these two are equivalent. These two are equivalent. If you don't like the way that that looks and you think it's cluttered, that's okay. You can redraw your triangle. I'm going to redraw mine like this. 20 degrees is a pretty steep angle. So I know that this side, I'm going to write a 3, is you get a number stuck in your head and it just keeps coming out with your pen. 15,000 newtons for the side. And I have a 20-degree angle. And what I need to solve for are my x and y components. You guys have any questions so far? Drawing triangles make sense? All right, and then to solve that, we're going to take a look at these. Our right triangle is right, or our right angle is right there, which means the 15,000 is our hypotenuse. The x side of my triangle is the adjacent side, and the y side is the opposite side. And so if I'm using my mnemonic, sine is opposite divided by hypotenuse. Cosine is the adjacent leg divided by the hypotenuse. Tangent is the opposite side divided by the adjacent side. For x, I'm going to use the adjacent side of the hypotenuse, so it's going to be cosine. And for y, I'm going to need to use the sine. So I don't know. I like doing them, whatever side of the problem they're on. So I'm going to start by solving for y. For that, I'm going to need to use sine because it's opposite hypotenuse. So I'm going to say the sine of 20 degrees is equal to y divided by 15,000 newtons. So y equals, if I multiply both sides by 15,000, 15,000 newtons times the sine of 20. Sorry about that. Uh, 40, ooh, that's not right. I accidentally hit divide instead of multiply. Try it again. I got like 43,000, which is not possible, right? Because I can't have a number bigger than 15,000. So 15,000 times sine 5,130 newtons. And then for the x side, since it's the adjacent and the hypotenuse, I'm going to use cosine. So the cosine of 20 degrees is equal to x over 15,000 newtons. To solve for x, I'm going to multiply both sides by 15,000. So x is going to be 15,000 newtons times the cosine of 20 degrees. I got 14,000 95 newtons. That seems like a lot. Is it reasonable? I think it probably is. This is such a steep angle that most of the force is going to be the side. Now, what that means is that there's only 5,000 newtons of that force holding that bridge up at that cable, which might explain why you either have lots of cables on a suspension bridge or you have a couple really big cables because they need to hold more tension in them than that. Any questions so far? No? You guys ready to let you try to do some? Me think. Yeah. All right. So keep in mind, guys, the thing you need to do first is think about how you need to create those triangles around your problem so that it makes it easier for you to solve them with trig. And then once you have it, if you think that it looks too cluttered, just feel free to redraw it. That's the easiest thing to do so you can see it a little bit better. Do you folks at home have any questions? All right. If you do at home, feel free to stick something in the chat and get my attention. Because I don't have the volume up very loud. Otherwise, I get weird echoes in the classroom. I'm going to let you guys go ahead and get started on those. I think that we've got about half an hour today and half an hour tomorrow. I think, let's see. We'll check on where folks are tomorrow. And if we need more time to work on things during our at home time, then we'll use that for that. Sound good? I don't want you guys to get stressed out about physics problems. We're going to kind of take this easy so that you guys are in good shape